So we have finished talking about mirrors, and we're about to start talking about lenses. So the good news is a lot of this stuff is going to rhyme. So here is a virtual image, and that turns out to be made by a biconcave lens, or a diverging lens. And that is well, I don't know, you tell me. That is an inverted real image. So this is the stuff that you guys are drawing in the abstract, how it looks in like real life. So virtual upright image, real inverted image. And these obviously are lenses. So it turns out that refractive elements can also make coherent images. And as I was saying before I interrupted myself, the good news is that a lot of the stuff that we learned with mirrors will actually be totally applicable mathematically here. So let's start by reminding ourselves of this kind of optical theorem almost, is that if an element could be a lens or it could be a mirror, has a focus, it can create coherent images. And what we've gotten through is the fact that mirrors, both plane mirrors and concave and convex mirrors, have foci and create coherent images. So you might be squinting at me and saying, like, but wait a minute, a plane mirror, I know it creates a coherent image. I look at one probably every day, but where's the focus? So for a plane mirror, where is the focus? Where do light rays that come in at infinity converge? Also at infinity. So in fact, a plane mirror has an infinite focal length. So what we're going to do is do the same thing with lenses. And the thing about lenses is they don't reflect, so we won't be using the law of reflection. They refract. So it's not the law of reflection that we got to worry about. We got to worry about Snell's law. Except we probably won't really worry about Snell's law. What we'll do is we'll argue that certain types of lenses should have foci, and then we'll actually take it without proof. Because what I'll go over at the end of this chapter and every chapter is all of the stuff that is kind of swept under the rug, or in some cases I kind of lied to you about, because that's the way that physics works, is a series of lies where you kind of like refine the thing you lied about and tell less of a lie at each sequential step. So let's say that I got a lens, and the point of a lens is that n is greater than 1. So this is something where n is greater than 1, and in fact this particular lens, we'll just say it's a biconvex lens. So it's got two convex sides, and they're circular. So technically what this is, in this particular instance, is spherical biconvex. So each one of these sides would be as if it was cut from a circle. And they don't necessarily have to have the same radius, and we'll get to that later. So I've got a spherical biconcave lens, and I'm just going to geometrically kind of argue the fact that this thing has a focus. And then we'll do the same thing with a biconcave lens. So what does it mean to have a focus? Well, what it means to have a focus is that light rays coming in from infinity, or parallel to the principal axis, so this is the principal axis. If I were to fold the lens over, it would fold over on that, come in and they get all, in this case, not reflected, but refracted through the same exact point. And so we'll kind of hand wave argue that. The proof is in the book if you want to look at it. Again, the way we're doing proofs is if it illustrates anything important, we'll go through it. If it doesn't, we won't. So here's normal. So I'm actually going to draw, I guess this is saying the center of that lens, which we'll call R1, would be here. So that would tell us where normal is. And if I'm going from, for instance, air into the lens, what would be true about the refraction? So I would refract towards, right? So if I go from fast to slow, I'm going to bend towards this. So if I looked at these little angles, so this would be theta air, and then this little one would be theta lens. Theta lens is smaller than theta air because Snell's law tells me that if the index of refraction goes up, then the angle goes down. So as a reminder, this is Snell's law. So if I go from fast to slow, then what needs to be true is I got to go from big angle to small angle. Right? So as the speed goes down, the angle needs to change accordingly, the sign. So bend towards the normal. Okay. So now I get to this second side, and I have a second refraction. So my second refraction would be based on this. I have R2, the radius of curvature for this back side, and I could draw a line out here towards the normal here. And this is something really neat. So I go from lens to air, so glass to air. I would bend not towards, but away from the normal. But this is the cool thing about the lens, is that if you look at the geometry of this, to bend away from the normal, because this normal is coming out this way, do I bend up or do I bend down? If I'm going to bend away from that normal, I bend down a second time. So in fact, I bend down once, partly because I'm going into lens and partly because of the geometry of this curved side. And then I bend down a second time as I leave this, and I bend at a bigger angle, but then the geometry of this normal says that I go down a second time. So that's my kind of hand-wavy, literally a sketchy argument, actually. And then we'll do a second difficult ray. And same thing's going to happen. I'm going to have two normals. I'm going to have a normal here. Because I'm going from fast to slow, I bend towards that normal. This is a little bit less severe than that, so I should draw it accordingly. So this normal might be pointed upwards. This normal would be pointed less upwards. This normal would be dead flat, and then these normals would be pointed down. So in fact, this refraction is not going to be as severe as the one up there. But it's still going to have the same properties. It's going to bend towards the normal a little bit, and then it's going to bend away from the normal on the refraction outwards, but it's the normal itself that changes because it's dictated by this. So obviously not precise. I just made it be what I know it's going to have to be. And that was 2. We need a third one because we want to do some, three rays need to be used if we're going to make sure we have a coherent image. So the third one and the third one only, I'll use the easy ray, which comes straight in. And I can verify that this should go straight through because if I extend a line from this radius of curvature along the normal, that's 0 degrees. And if I extend one along this normal from there, that's 0 degrees. So, aha, we have the sketch of the idea that we should have a focus. Right? You can prove this, and proving it actually for spherical lenses is a bit tougher. It turns out that spherical lenses don't actually have a focus. They have an approximate focus, provided that this is very, very thin. So that's part of the reason that we skip the proof. So in fact, for thin lenses, and what a thin lens is, so this thing is cut from 2 spheres. So here's R1 and R2. It's numbered backwards from there, but it doesn't matter. So this would be the sphere from which this is cut, and this would be the sphere from which this is cut. So each side of these is a perfect spherical shape. This lens has a thickness, D. So what a thin lens is D, the actual thickness, like if you measured this with calipers, is much less than R1 and R2. Then the lens has a focus. Okay. For mirrors, the focus was given by just R over 2, which is really pleasant. For lenses, that's actually not going to be the case. So in fact, if you think about it, what could the focal length of a lens depend on? Well, it's got to depend on Snell's law stuff. So it depends on not only the geometry of this, R1 and R2, but it also depends on what it's made out of. So if I have something that's really weakly refracting, this focal length is going to be out here. If I have something like diamond that's really strongly refracting, it's going to be farther in because those light rays are bent more severely. So we'll cover that later. That's the so-called lens maker's equation. But for now, what we have is a focus, right? So thin spherical lenses have a focus. And if you want to see it, the lens maker's equation would tell you that the focus is located here. So actually, we'll just do the air one first. So exactly all the things that you would expect. It depends on the index of refraction of the material and the geometry of the material. So this is the lens maker's equation. We'll cover it in detail a couple lectures from now. So here's a good check-in to see how well you're doing with the idea of Snell's law. So let's do the same thing, but for a biconcave lens. So this is a biconcave, which is to say both of these sides hold water. Thin, which is to say that the actual thickness of this lens is smaller than the two radii of curvature. Spherical, which is to say it's cut from two spheres. So that and that would be spherical depressions, like you rested a ball inside of it and it would fit perfectly. And lens, it's something that's transparent and refractive. Okay, so I'll put a principal axis here. Feel free to pause and try to work this out yourself. I'll put an R1 here and an R2 here. And super quick, we'll make the same exact argument, but we'll make it backwards. And just so show the property of the focus for a biconcave or diverging lens. Okay, so let's do the easy ray first. So I'll go in perfectly along the principal axis. The first time I refract is when I go from air to lens. That's this radius, so this is the radius of curvature there. That's just dead normal. I'm hitting the thing dead normal. Easiest Snell's law possible. My angle of incidence is 0. This entire left-hand side is 0. My angle of refraction is 0. And then likewise for that. So this passes straight through. Love that ray. Okay, now we get a little bit more interesting ray. So let's go up along maybe, let's do all the way at the top. And you'll see why this is all the way at the top. Okay, so which way am I going to refract here? I care about the normal. This radius has center there. So I would draw this all the way out. There's my normal. Am I going to bend towards or away from that? I'm going from air to lens, so I'm going to bend towards it. This angle is going to be bigger than that angle. So, because of the geometry, I don't bend down, I bend up. And then here, I'm coming out here, so there's normal. And I'm going from slow medium to fast medium, so I'm also going to bend away from normal, so I bend up a second time. So now you see why this is a diffracting or a diverging element. And I could do the same thing here, so draw a third ray just for good measure. And the only difference, so these are going to bend up and bend up a second time. The only difference is that the normals that I would draw coming from R1 are a little bit less severe in angle. So my bends would be a little bit less severe themselves. So yeah, and yeah, maybe. Okay, so I get something that looks like that, and I'm going to clean it up, and then we're going to make a conclusion. So does this thing have a focus? The light rays coming in from infinity converge somewhere? Not when I say it like that, but in fact the way we started this video is by pointing out the fact that, I just literally showed you a diverging lens and it was able to coherently show that image of the word lenses. So in fact, likewise for convex mirrors, the focus is the place where either light rays from infinity converge or appear to have converged. So what I'm going to do is I'm going to take these light rays, and if I trace them back, this is where they appear to have come from. So if you're an eye out here and you're seeing these light rays spread out, you're like, oh, it's as if they came from there. So this is a focus. right? And this is only approximately true for, again, the thin lens thing. So if you actually, and we could do it, if you made these not from spheres that have a circular profile, if you made them from paraboloids, which have a parabolic profile, they would be perfect. But for us, spheres are just like easier to make and have been historically. And I'll talk a little bit about the lies at the end of the chapter, so the idea of spherical aberration and diffraction. So both of these things, thin spherical lenses, have foci. And in fact, if we were to mix one, might be your next question, and have a convex side and a concave side, that's a great marker. Woof. Those actually would have a focus as well. So we'll just write that as a note for now and talk about it when we talk about the lens maker's equation. So these are what are called meniscus lenses. And a meniscus lens might have a convex and a concave side. So this side would be concave, and this side, pretend my drawing doesn't stink, might be convex. So concave, I can actually literally hold water in it, and convex. So convex and concave. So these are so-called meniscus lenses. In fact, if anybody wears eyeglasses, I suspect some of you do, those are actually meniscus lenses. Okay. So what we'll do in the next video, this is just kind of an introduction to the idea of this and why we're able to basically port all of the stuff that we did with foci and the mirror equation to this. They do have focuses. We'll not derive, but then start using the mirror equation, but for lenses. And literally the only thing that changes is its name. It's now called the thin lens equation.